Now let's apply Kirchhoff's rules to illustrate them. Let's apply them to first a simple circuit, which is a single loop circuit, but with two electromotive forces rather than one electromotive force. And this is the circuit shown here. Evidently here R1 and R2 are connected in series because the same current is threading through them, but we cannot apply the basic circuit equation that we have learned before because we have here two electromotive forces. But we can derive a simple result by applying Kirchhoff's rules, and in this case what we apply is the voltage rule or the loop rule, which says that the sum of the potential across an enclosed loop is equal to 0. So indeed, let me start at A, for example, and come back to A. And I can traverse it the way that I like. Okay? You either take it clockwise or you can take it counterclockwise. The second thing is, what about the current in the circuit? Which direction should you choose for the current? It is up to you. I mean, we don't know what is the current. We want to find the current, but we don't know what is direction. It might be flowing clockwise, it might be flowing counterclockwise. You choose it at your convention. The result is independent of which direction of the current you choose. And the direction in which you transverse the loop need not be the same direction as in which the current flows. So I mean, here it's just a coincidence that I am going counterclockwise and the current is flowing clockwise. I could easily go counterclockwise when I transverse the loop. It doesn't necessarily I don't necessarily need to go in the same direction as the direction of the current. Okay? This is not necessary. So I assume the current is clockwise. I assume that I start from A and go A, B, C, D, E. Okay? And this loop rule says add up every potential across any circuit element that you encounter, taking into consideration the correct sign. So when you go from A here, you first encounter the electromotive force, and you are moving, as you transverse this way, you are moving from the negative to the positive terminal, that is from lower potential to higher potential. So the delta V in this case is positive, so you substitute plus E1. Then you encounter the 8 ohm resistance here, and you are moving, as you move here, you are moving along the direction of the flow of the current. So the potential drop, in this case, the potential across this, as you traverse it, is actually negative. You are moving through a potential drop in this case. So you say minus I times R1. Okay? And then you reach this. Now here you are traversing this 12 ohm resistance from the potential, from the terminal, or from the terminal which has the higher potential to that which has the lower potential. So in this case, you will be moving across a potential drop. So it's minus E2. And then you come to here, to this point. Now here again, you are moving through R2, and you are moving along the direction of the current. So it is again a potential drop. So minus IR2, and you come back to A. So all of this is equal to 0. So once you have this, then you have the equation that is needed to find the current, because the electromotive forces are known and the resistances are known. What remains is just to put the current on one side and then substitute the figures, and you get the current as minus 0.33 amperes. Now here, the important point, this minus sign tells you that the actual current that will flow in the circuit in view of this configuration of the resistors and the electromotive forces with this polarity is not in the direction that you have assumed, but the negative sign still, it should be in the opposite direction. So the direction actually of the current is counterclockwise, and the minus sign reflects this. Okay? Had you started with the current assumed to be flowing counterclockwise, then things would have changed here, and you would have got a positive sign rather than a negative sign here, because your current, you assume the current in the same direction as the physical real current in the circuit. So this is the simplest rule of the circuits where you can apply Kirchhoff's rules, which is a single loop circuit with more than one electromotive force. So you have two. You could have three also. It doesn't make a difference. Now, let's assume that the polarity of the circuit of this electromotive force have been switched. So rather than having it this way, it is switched. Okay, so this is the negative, and this is the positive. In this case, what will happen? Well, I could have kept the current the same direction, I mean clockwise, but let me assume that I also have switched the direction of the current. In this case, how would this affect the circuit? Would the current change in this case? Well, again, apply the loop rule. I start in this case from B and come back to B. Okay. Now, when I'm flowing in this direction, I'm flowing against I'm talking it clockwise now, counterclockwise. So BADC. So you are going BADC and coming back to B. So when I move in this direction, I substitute this as positive because I'm transversing this from the lower to the higher terminal, so E1. Here again, moving along the direction of the current, so it's minus R2I. Here again, along from the negative to the positive, so plus 12 volts. Here again, from along the direction of the current, so it's minus R1 multiplied by I. Substitute for the E's and the R's, and you get E1 plus E2 divided by R1 plus R2. This is the current, and you get this the current to be equal 1 amperes. Here I don't have a negative sign. I just assumed the current in this direction. Had I kept my assumption as before that the current is clockwise, then in this case I would have got a minus 1, and this would tell me, well, you have to, your current is actually flowing counterclockwise. Okay, so my current in this case is 1 ampere. Now, the general rule for a single loop multi-EMF circuit is the following. Sum of all electromotive circuits, electromotive forces with correct sign in the loop, you take any loop, traverse it the way that you like, assume current in any direction that you like within that loop, okay? But go with the correct sign convention across the electromotive forces. So sum them all, as we have done here. Here, the sum was E1 minus E2, because that was the sign convention. Here, the sum was E1 plus E2, according to the sign convention. Divide by equivalent resistance of the whole circuit. Why? Because R1 and R2 in this case are what? They are two circuits that are connected in parallel, in series, and the equivalent resistance is actually R1 plus R2. So that's the equivalent resistance. You might have more complications here, more complicated resistances here. So you might have another resistance here in parallel and so on. So find the equivalent resistance of the whole circuit. It will be in the denominator in this case, and then apply this rule, and you will get the current in such a circuit, which is the simplest case where you can apply Kirchhoff's loop rule. Now, a more complicated example, which is a multi-loop circuit. So if you look at this circuit, for example, here, this is a multi-loop circuit. And actually, it's a 3-loop circuit. It looks like 2 loops, but actually, it's a 3-loop circuit. The first loop is this. You can start at E, for example, and come back at E. The second loop is this. You can start at B and come back to B, or at C. And the third loop is this, actually. The outer loop, this one, is the third loop. So this is a 3-loop circuit, okay? And I am given the electromotive forces, I'm given the resistances, and I want to find what will be the current in each electromotive force or in each resistance in this case, okay? Now, what I do is I assume at each junction here, I assume current. And I call this current, so I1, I2, I3, whatever is that. So for example, look at junction C here. At junction C, I assume that there is a current coming into junction C from the left. I call it I1. I assume there is another current I2 also coming from here, and another current, and I3 is leaving in this direction. Now, why I assumed I1 in, I2 in, and I3 out? Arbitrary. You could have done any combination. You could have assumed I2, I1 coming out, I2 going in, out, and I3 coming in. You could have done that. Okay, it's just arbitrary choice. At the end, the signs of the currents will tell you which current flows really in which direction. Okay, now so in this loop, in this part, you have I2, I3 flowing. So at B you have I3 coming into B. You have I1 leaving B again, because I1 is flowing through these two circuit elements, the EMF and this. And also you have I2 at B leaving B, okay? Because, you know, this I2 is the single I2 passing through all these circuit elements, okay? It doesn't branch to anything else, so it should be I2. So here also, actually, at this branch, you have I2, I3 coming, I3 coming in, I1 coming out, and I2 going out again. So you apply this junction rule here at C, which is I1 plus I2 minus I3 equals 0. Now, if you apply it here, you will get the same result, maybe multiplied by an overall minus sign, but we'll get exactly an equivalent result. Okay, the same equation, but maybe up to an overall minus sign, but no new information. Okay, so one equation is needed actually in this case, which is as far as the junction rule. So in this case, I apply it to this junction C. Okay, so I need to find the currents. I have I1, I2, and I3. These are the three unknown currents. I don't have more currents because these are the currents flowing in all the various circuit elements in this case. So what's the next step? Well, the next step, apply the loop rule. So for example, I start with the first loop. I take the loop A, B, C, D, A. A, B, C, D, A. Okay, this loop. Again, you start at A, up to B, there is nothing here. I have a 10 volt plus 10 volt potential rise across E. So this is 10. And here, this is a 6 ohm moving along the direction of I1 that I have suggested. So it's minus 6 I1. Continue here, there is nothing here. Here I'm moving with I3, because in this loop now, I3 in this resistance, I3 is passing, and I am moving in this direction, and this is the same as the direction in which I3 is falling. So minus 2 I3, and then I come back to B, so I say equal to 0. So this is for this loop. So I have one more equation. Okay, since I have three unknowns, I need a third equation. I take now the other loop, B, E, F, C, B. So I start at B and come back to B, again moving clockwise in this direction. So now here you are moving along I2, because I2 is flowing in this direction. Here it's flowing, so it's minus 4 I2. Here minus 14 volts. Here you come back, there is nothing here. When you move here, you are moving against, when you are traversing the loop in this direction, you are moving from C to B. You encounter this 6 ohm resistance, and you are moving against the current. So as you cross it, you are crossing a potential rise in this case. So it's plus 6 times I1. Here you have a potential drop from the higher to the lower terminal or plate of the battery. So it's minus 10 volts, and this is equal to 0. You can add up these two together. So you'll get minus 24 plus 6I1 minus I2. So now I have the three equations and three unknowns. This is equation 1, this is equation 2, and this is equation 3. What remains is what? The algebra of solving three equations with three unknowns simultaneously. Okay? What we do is first we substitute for I3 from this equation as I1 and I2, and substitute this into this equation, substitute for I3 in this equation. So you get this equation in terms of I1 and I2, and I already have this equation with I1 and I2. So I multiply that last equation by 4, and I multiply this equation by 3, so that I can, in this way, this will enable me to cancel when I add them up. I add up this equation and this equation. I can cancel out I1. So I get a single equation, an equation for a single unknown, which is I2. When I solve for it, I get I2 equals minus 3 amperes. So I have found the first unknown, which is I2. Now I substituted this either in this equation or in this equation, whatever you like. And when you substitute it in this equation, for example, I2, you get I1, which is 2 amperes, and you get I3 from the junction rule, you get I3, which is minus 1 amperes. So as we can see, I3 minus 1 amperes tells us that I3 actually should be into C physically. Okay, I1 is okay, so it's into C. I2, you remember, we got it as minus, so minus 3 amperes, so I2 actually should be flowing in this direction. So these are the solutions to the circuit, and I have found I1, I2, and I3 that are flowing in this circuit.